Good morning, everyone. Thank you all for being here. We really appreciate it. My name is Ron Ashburn. I'm the Executive Director of the Association for Iron and Steel Technology. It's my honor to welcome you all to AISTech and to the Howe Memorial Lecture, representing the opening session for this year's conference. Now, before we begin, I do want to point out our emergency egress route in case we do need to leave this room. You're just going to go out the doors you came and go down one level anyway and out onto the street. And although this is the opening session of AISTech, things actually kicked off yesterday with our AIST Foundation golf outing. We had a full flight of golfers, and they helped raise over $30,000 for scholarships and academic grants that help our industry prosper. And starting this morning, this year's conference will include 550 technical presentations. This is number one, representing over 1,500 authors from 30 countries. I'm also pleased to report that we have an excess of 8,000 attendees this year, and we thank all of you here this morning with us in Nashville. Now, tomorrow morning at 8 a.m. it will be the President's Award Breakfast featuring Dick Tietz. He's the co-founder of Steel Dynamics. Then on Wednesday morning at 10 a.m. will be the town hall with 6 industry executives discussing the challenges and opportunities of the industry. We have Ron Bedard from ArcelorMittal, Dan Cowan from Steel Dynamics, Dan Colleen from U.S. Steel, Nick Kohlhaas of Cleveland Cliffs, Ben Coing of SSAB, and Trevor Saunders from Nucor. It's a can't-miss event. I encourage you all to be there. There's a lot of Ks in that, and the session chair is George Koenig, also with a K. So there's something special happening this year with the town hall, and I encourage you to visit that on Wednesday. So all the plenary sessions, including this one, are being streamed live, and we hope that this format provides everyone with an opportunity to participate no matter where in the world you may be located today. And running today through Wednesday is the exposition. It's our largest ever in all aspects. 723 companies are represented in the expo. We'll also have an attendee reception in the expo hall tonight and tomorrow night, Monday and Tuesday evening. They will run from 5 to 6 p.m. And then our Chevrolet Silverado pickup truck giveaway will be Wednesday afternoon at 2:30 p.m., but you have to be present if you want to win that. Again, that's Wednesday afternoon at 2:30. Now, before we begin, I would like to point out that you need a blue badge or an orange student badge to attend any of the technical presentations this week. If you don't have one, please go to registration and they'll help you obtain one. Also, please mute all cell phones while you're in a session, and remember that the recording of our presentations at AISTech is prohibited. Now, it's my distinct pleasure to introduce the 2025 Howe Memorial Lecture. The lecture was established in 1923 to honor Henry Marion Howe, and as history tells us, Dr. Howe helped turn steelmaking from an art into a science with his gift of observation and deduction. He studied the breakthroughs of others. He added to them with his own investigations to help establish the field that we call metallurgy. And over the last century, the Howe Lecture has welcomed the best and the brightest minds to the conference stage to share their insights. The extraordinary work of all Howe lecturers, past and present, has shaped our modern understanding of steelmaking as a science, and their work will undoubtedly inspire innovation well into the future. Now, additional information regarding the legacy of this lecture has been looping on the screen, including the biography of this year's recipient, Dr. Tadashi Furuhara. He is a professor at IMR, the Institute of Materials Research at Tohoku University in Japan. Time permitting, we will have a Q&A session at the conclusion of his lecture, and we're going to formally recognize Dr. Furuhara tomorrow morning at the President's Award Breakfast. His lecture this morning is entitled Roles of Thermomechanical Processing on Microstructure Control of High-Strength Steels. He's a compassionate leader in the field of metallurgy. He's a true champion for steel, so please join me in welcoming Dr. Tadashi Furuhara.
Thank you very much for a nice introduction. Good morning, everyone. I'm Tadashi Furuhara from Tohoku University. So it is it is great honor for me to receive this prestigious award and get the chance to give this excellent lecture. So this is the title. I'd like to explain before the really giving the main topic of this talk. Okay, rather not easy to see the both screen. Anyway, I'd like to show you the something about the Professor Howe's work. This is the famous textbook, Metallurgy of Steel and Cast Iron, published in the 1916. Our institute published founded in the also 1916. We got the same year we got this volume of the textbook. So here the iron carbon phase diagram and showing the now we all know about the nomenclature of all the phases in the phase diagram, but this is Professor Howe the work, one of the best work in his career. And of course, you know that the phase transformation in solid state in iron after the cooling down from the melting temperature, so BCC, FCC, and again BCC. And there the one transition temperature, so-called A2 temperature, that is the magnetic transition from the for iron, pure iron. There was a debate, so-called beta iron there. And the previous phase diagram, there was the region for beta iron and alpha iron for BCC. So it was there was a long discussion about from the autotrophist and the carbonist between, and Professor Howe belonged to the carbonist. And our first director of our institute contributed a little bit about the distinction of this phase transformation, Professor Honda. And he measured the thermal measurement and find the continuous change in the differential curve. That means no really first order, the kind of second order phase transformation. Later, Westgrain showed the clearly by X-ray diffraction and no crystal structure change. So after that, here, as I explained in the previous figure, there the set of the phase diagram by Robert Austin and Rosenbaum. Then Professor Howe's work on the nomenclature of the phase diagram is settled. Our institute also established in 1916. So now the over 100 years. And we have we have the mission to perform the fundamental and applied research on the materials. And we have about 100 professors in our institute. And of course, related to the steel research, about Professor Honda, and also Professor Nishiyama with Mr. Martensite in Japan. And also the famous Professor Kaya, who found the magnetic isotropy of the pure iron. That is the fundamental for the current technology of the grain-oriented electric steels. So my work, my research group started from 2005, and we belong to we do this kind of cycle processing, the other development and processing design and microstructure characterization. I work on the fundamental issue related to phase transformation, precipitation, and also deformation and recrystallization. As a result, and also we work some working on the property control by using the thermomechanical processing, and it's the main topic of today's lecture. And also we work on the also thermochemical processing, so-called nitriding. So as a physical metallurgist, I really feel honored to see the previous physical metallurgist list of that. So I really feel really honored for me to get this award. Very special for me. So main topics. First, I'd like to mention about the history of the thermomechanical processing of steel. Of course, we know a different kind of the steel product from sheet, a thick plate, and pipe, and burr, and gear, or kind of things. To form this kind of product, we use thermomechanical processing. So here, I show you the different kind of the phase transformation product. I mean, ferrite, ferrite, and bainite, and martensite, putting on the phase diagram. Okay, here. Phase diagram of the iron carbon, temperature versus carbon content. So when you look at the from high temperature to going down to low temperature, we have the increase in the tensile strength like this. So very important to control the transformation temperature to produce the high strength steels. So this is the classification of the thermomechanical processing. Of course, we apply the deformation. So when we deform the materials, before transformations, during transformations, after transformations, so we separate those in the processing. The target of the phase transformation is diffusion transformations, ferrite and pyrite, or martensite transformations. So the famous one, of course, the controlled rolling. We know now the TMCP combined with accelerated cooling. And for applying the martensite before transformation, we call that direct quenching or osforming. And during transformations, of course, they are the, it's not really, okay. It's not really coming out. Okay, here you go. Ice forming, or that's the, sub-zero transformation or trip. And after transformations, we have the called drawing, like after patenting for high carbon steel, and also the now there also malforming or temp forming is applied for the martensite after deformation after transformations. So this is the change in the typical thermomechanical processing of the steels over past 50 years. So displacive transfer, we really started from displacive transfer martensite and applying for the high alloy steel for osforming and trip, invented by the Professor Zake in Berkeley. Then after that, we all the main steel product goes to thick plate. We apply for the diffusion transformations, ferrite, pyrite, by applying the control rolling and accelerated cooling in 70s and 80s. Then again, we go back to the in 90s, and 2000 we go to the direct quenching and also the okay, here you go. Osforming and trip. So we try to increase their strengths, particularly for sheet steel application. So we started from high alloy for osforming trip and low alloy for microalloy Hasra. Then again go back to the low alloy steel for applying the this kind of the mechanical processing. Strength definitely change, of course. And first we have very high strength, over 2 gigapascal. Then go to the lower strength product for diffusion transformation. Then we again go back to the higher strength now. So this is the main research and development, the low alloy steels in 1780s in Japan. For thick plate, of course, TMCP is explored by replacing the microstructure property from the ferrite and pyrite to the bainite. For topic for the sheet steels, in between 60 and 80s, we have the very soft iron is very important. So industrial free steel is used developed for body design. And then after oil crisis in 70s, and also the importance of the crash worthiness is focused, we explore the higher strengths. So toward the March phase series in 90s and 2000. So I'd like to introduce the first national research project in Japan. You may not really are familiar with that over, let's say, 20 years or so. Main topics for steel project for the physical metallurgy-based one. In our late 90s, the early 2000s, we have the ultra steel project and also super metal project. This is for academia and this is for industry. And both of them focus on the ultrafine-grained steels for superior strength and toughness, and both of them. So, and after this project, we had another project, the nanometal project, in the early 2000s. So this is the nano-size precipitation is used for high-strength steels. Mainly of the transparent copper is try to use a little bit more for strength, better strength. And later, R&D fundamental for forging and also welding. And for forging materials, medium carbon steel, they are the usage of the alloy carbide, mainly vanadium. For ultrafine grain, what is the importance of ultrafine grain of the ferritic steels? So of course we know strengthening can be obtained by their Hall pitch relationship. And also toughening in terms of the ductile brittle transition temperature, we can lower this transition temperature as a function of the grain size. So here, the plot of against the for ferritic steel strength and versus the grain size. And of course, as you decrease the grain size, we have an increase in yield strength and high tensile strength. And transition temperature decrease like this. So at the beginning of this national project in late 90s, the normal transformation ferritic grain size is about 10 microns. Applying TMCP, we can goes down to the 5 microns. Now, but if you try for the grain size less than 1 micron, we can actually double the strength and also really low transition temperature we can obtain. So that was the main target. So this is the industry-oriented national project, steel, super steels, super metals project. And in the various heat treatment, thermal processing explored, then we obtain ferrite grain size less than 1 micron. So this is normal TCMT, and 5 microns is the target, and the practical use. And by applying the lower deformation temperature in the metallurgical austenite field, and also applying the larger strain, then we can get the ultrafine grain. And this is the case of the deformation applied in two-phase field in austenite plus ferrite or ferrite plus cementite. And third one is the, again, deformation lower than the A1 temperature, and adiabatic heating, we can increase the temperature by applying the more strength. So interestingly, we found in this project in Japan, new phenomena. For this, for type 1 case, we mainly have the dynamic transformations. And for this case, of course, this is two-phase field deformation. We can have the dynamic recrystallization of the ultrafine grain to obtain ultrafine grain materials. In this case, as I mentioned, low temperature and applying the heavy deformation, we can have the sharp increase in that product temperature and get the adiabatic heating reversion. By having such a new phenomena, we could reach to the ferrite grain size less than 1 micron. So dynamic recrystallization. Of course, this is a very nice phenomena because grain size can be obtained, defined by processing condition, strain rate, epsilon dot, and temperature in terms of the Zener hormone parameter. And however, when we take a look at the flow stress at the higher temperature or lower strain rate, we have the relatively low flow stress. And the recrystallization initiating strain is small, and also finishing strain is small. However, if we go to the larger Zener hormone parameter value, Z value, we can have such critical strain increase to the higher strain level. So although we can obtain ultrafine grain materials, but we need to apply heavier deformation. So that's why severe plastic deformation is very important now. Also, there's a discussion about the recrystallization phenomena from discontinuous one to continuous one. By applying the further strain down to go up to the severe plastic deformation level, we can have the from subgrain structure change to the ultrafine grain structure by increasing grain misorientations by absorbing the dislocation at the grain boundary. And dynamic recrystallization is, of course, given the textbook, we can have the subgrain for continuous one, particularly the subgrain change to the high angle grain boundary. And there are the two different curves for the grain size versus Z parameter. This is the recrystallized grain size, and this is subgrain size. But applying the further higher strengths, we have the really the mixed region for the between two lines intersected. Now we are having the transition from the discontinuous recrystallization to the continuous recrystallization. Dynamic transformations is transformation during deformations. This is typical TMCP. Of course, we have the deformation in the recrystallized region of the austenite and the non-recrystallized region of austenite, and the cooling down, we have the transformation. However, when we look at the for dynamic transformations, we have further deformation below transformation temperature. We have the deformation, phase transformation during deformation. As a result, because of the stress-strain effect, we have the change in the stability, phase stability. We can transform the product above the transformation temperature. But simultaneously, we have the dynamic recovery or recrystallization of the austenite. So as a result, we have the very complex microstructure change We have depend on the compression or processing condition. We have the very complex phenomena in terms of the dynamic transformations. But anyway, we have the new phenomena, transformation during phase plastic deformation. So as I mentioned already in the national project, severe plastic deformation become more important. So this is the, of course, shape invariant plastic processing method, like ECAP or high pressure torsion, or multi-directional forging, or accumulated roll bonding. All of these plastic deformation processing, we can apply very severe, high strain in terms of severe plastic deformation. Epsilon is over 4. So by having such a severe plastic deformation, we have the very interesting phenomena. We can increase the pure iron to 4 times higher in tensile strength, yield strength. And also, usually we expect the work hardening and give us the lower ductility. However, by having the mobile dislocation, high density of mobile dislocation, actually we have the better ductility as deformed condition. However, if we anneal that, we lose the ductility. The other case is the caliber rolling, and they're applying the severe plastic deformation. And this case, ultrafine grain fibers, texture. Then we can really, going down the low temperature, testing temperature, we have the actually increase in toughness. So this is called, because of the delamination toughening, we have the along longitudinal direction, we have the preferred fracture. However, it is difficult to penetrate such cracks over thickness. So that's why we have this kind of the very peculiar, peculiar phenomena in toughening. Okay, so I'd like to here make the emphasize on the also controlled heating after thermomechanical processing for strengthened steels. So of ultrafine grain case, of course, in 60s, we know rapid heating and quenching technique proposed by Grange is the company produced the ultrafine grain of the austenite. So as a result, or by quenching, we can get the ultrafine-grained martensite steel. This is one case to get the austenite grain size less than 10 micron. The other case in 80s in Japan, Professor Tokizane applied the cold rolling and reversion of the martensite. So by having that, we can reduce the austenite grain size down to the 5 micron by having the particle pinning, maybe 2 micron or so. We also apply that in this case for modeled steel and applying the I lost the here you go. By applying the particle pinning of barium carbide, so we can go down to the austenite grain size less than 5 micron and at around 2 to 3 microns. And after phase transformation, we can go down to the 1 to 2 microns. But for this, that is for low alloy steel. Reversion takes place quickly. But for high alloy steel, like let's say 9 nickel, with the important cryogenic thick plate applications. Here's the phase diagram with the austenite and ferrite. And this is two-phase field. So this is the cooling down. And we have the, of course, phase driving force for phase transfer forward transformations. And they are the case of the reverse transformation like this. And they are the characteristic lines for Tohoku T0. Austenite and ferrite have the same energy. So below that, for forward transformation, we have martensite, driving force for the martensite transformations. The above that, also, we can have martenstic reversion, although we have the more diffusion occurring at high temperature. So when we have the such martenstic reversion, we can get the good grain refining by reversion case because of the this so-called austenite memories phenomenon is happening. So this is the initial martensite structure. This is the after reversion and quenched. We have the same austenite grain size and almost same, a little bit refined for the martensite structure. But anyway, we have this kind of austenite memory effect is prohibiting the grain refining during the reversion for high alloy steel. So we have to be careful on that. Also, the summer cycle is welding is very important, you know. So we have the different kinds of the some figures missing. Sorry about that. Anyway, welding is having the difficult. We have this different kind of summer cycles. Depends on the place of the along the thickness. So also rapid heating can be also important for tempering case of the martensite. Tempering of martensite is, of course, we know precipitation of the superstructure carbon occurring as a precipitate, and also the recovery of the high dislocation density in martensite takes place. But when we apply rapid heating tempering, we can get the finer dispersion of cementite, and also retain the little bit higher dislocation density. As a result, we can get the higher strength and also better toughness by applying the this kind of the heat treatment. Whether you can use induction heating in the line, and this is already found in the 80s by Kawasaki, and by combining both induction reversion and also induction tempering, and we can get the finer grain size and also the better strength and toughness balances. So this kind of controlled heating, rapid heating, is very good at the better properties. Now, of course, here, of course, all over the world, additive manufacturing is popular, and of course, for the also the steels, relatively for high alloy or high carbon steels, we have a lot of the works done in the applying such thermal cycle in the additive manufacturing. There may be the several product, and perhaps this merging on the high carbon steel, we can have the phase transformation takes place. So during the thermal cycle during the additive manufacturing, we may have the actual grain refinement by controlling reversion treatment. This is the one example for this is authentic stainless steel, and we have the very nice aligned structure and the during the laser powder bed fusion. And of course, we know now there are different characteristic dislocation structure as well as the elemental segregation during this kind of thermal cycles. I'd like to introduce one nice work done by the Professor Nakano in Osaka University in Japan. Actually, they are controlling the heating temperature, and they can actually change the texture by applying the such nice reversion, heating control. So this is also, it's obvious the controlled heating is very important for additive manufactured steel too. Of course, now all of us know reversion is very important for high-strength sheet steels for the intercritical annealing, starting from the cold rolled sheet steel. So for hot rolling route, we have the simply phase transformation in ferrite transformation, and by ose tempering, we have bainite transformations. So we have the characteristic retained austenite. And of course, the size really varies. It depends on the place. And also for reversion case, we have the granular one and also acicular one. Depends on the initial structure, but we have the different kinds of the morphology of the reverted austenite. So that kind of morphology is dictated by the crystallography of the phase transformations. And so that morphology is affect on the phase stability and diffusion or alloy partitioning. And that is same for the reversion case. And the crystallographic character is very important. We've been working for a while and working on the defining the carbon enrichment in the untransformed austenite and for chip steel and also reversion case. So for the chip steel case, we have the larger one, we have the lower carbon content. For the finer one, particularly the film-like one, if we get that, we can have the higher carbon enrichment. But actually, the microstructure, we have the variation of the carbon enrichment in chip steel heat treatment. So gamma austenite size and morphology affect carbon enrichment and phase stability of retained austenite. For the reversion case, for granular one, we do not have the partitioning of manganese silicon substitution alloying element. However, for the acicular one, when we start from the martensite or bainite initial structure, we can have the slow interface migration, and macroscopic manganese and silicon is all for partitioning. That also changed the carbon content eventually. So morphology is very important in the actual the chemical composition and phase stability of retained austenite. Here also the two methods accelerate granular austenite reversion. And one is for the using tempering, rapid heating, and the other is pre-tempering. And by having such pre-treatment, we can have the granular austenite formed during the reversion, intercritical annealing. Recently, let's say 10 years or so, during reversion or intercritical annealing, or after that, high temperature reversion, we particularly medium manganese steel or something, we can have, we tried all the researcher focusing on the use of the manganese heterogeneity and for better strength and ductility balance. And this is the example by the Monash people, and they started from the partitioned pyrite. So with the medium manganese steel, I think. We have the manganese enrichment in cementite. After a complete reversion, a short time, let's say, and we can have the austenite and also the martensite lamellar structure. So by having such a microstructure, they succeed to obtain the higher strength by losing not much in ductility and also large work hardening. Several other examples in Germany for the trip case, and in Japan, core and shell type retained austenite, and one from China, and so-called flash annealing is used to have the control the manganese heterogeneity in the reverted austenite. So this is the area academia is focusing on now. I think also the lamellar structure itself is very interesting in terms of the better strength and ductility balance. This is the one big project in Japan, laminated structure. Martensite is covered by soft iron. And actually, when we compare with the banana curve, they succeed. Professor Koseki in Tokyo University, they succeed to get the better strength and toughness balance. And this is for the, of course, famous nano-bainite, lamellar, austenite, and bainite structure, produced by the Professor Harry Badeschi and also Professor Francesca Cabrera, and they obtained very high strength and very nice ductility. So those two are typical lamellar structure, nano-lamellar structure for very high strength and very high ductility. Of course, we know cold deformed ferrite can produce such microstructure. And this is our case. We apply the heavy cold rolling. We can obtain the cementite lamella is elongated parallel to the rolling plane. And we can get the similar one starting from the duplex stainless steel after hot forging and cold rolling. For the this lamella cold rolled ferrite case, recently in Japan, research group found hydrogen can be trapped at the cementite ferrite lamella interface. And actually, the better hydrogen suppression of the hydrogen enrichment. So this may be very interesting research area in the hydrogen enrichment suppression. Okay. Recent research projects at the end. I'd like to introduce a little bit more in Japan. And one is elemental strategy. We've been working on in Japan, government support on this kind of subject. Of course, the resource poor country like Japan is very important to perform this kind of project. So elemental strategy initiative, research initiative set at the Kyoto University and explored for 10 years. For better toughness, strength and ductility balance. Main output is a fundamental one, is a new plastic enhanced ductility concept. By having ultrafine-grained materials in magnesium, copper, or iron, or aluminum, we can change plastic deformation mode from strip to twin or martensite. So this kind of things we can control the strength and ductility balance. The other important part is, of course, advanced characterization technique is advanced, really developed during this kind of field. Another one, this is the, supported by the Ministry of Economy, and so-called ISMA project. And this is for much materials project. Of course, we have the different kind of strengths for automobile applications. So also we have the something aluminum or iron has been bonded. So much materials and joining is very important. So first 5 years and second 5 years, we have two terms. For steel, for first 5 years, there were target on the 1.5 gigapascal and 30%. Let's see. 20% in ductility. And after 5 years, the target is achieved. And so, after the later 5 years, they are focusing on the more the fundamental issue and joining. The other thing is the cabinet office supported material integrations, similar to the ICME in US. And so, particularly for the fundamental technology development for the inverse design. And materials integration and its implementation is a so-called MINT system is set at the NIMS in Japan. And that is for prediction module for the process microstructure and properties. So application is for the fatigue or join and I think creep and also hydrogen enrichment. So that kind of things have been done recently in Japan too. Now, new project starting 3 years ago. Tohoku University lead this, our university leads this project on the environment, extreme environments for structural materials. So RISME, we call that. So that data-driven structural materials for the better life. And 3 subjects, high-strength hydrogen resilient steels, and better fatigue resistant for surface hardened steels. The other is the super heat resistant materials. So we have much institutional project of that. Our group is working on the data-driven prediction of the fatigue performance of the surface hardened steels, led by my colleague, Professor Miyamoto. We're trying to develop the integrated system for prediction of the fatigue and also the hardening profile from the processing, alloying design, and microstructure, and also the properties. So for that, we're using machine learning and also physics-based model try to be developed. Also, that's the kind of things we are working in Japan recently for a national research project. At the end, I'd like to explain a bit about the ISIJ, Iron Steel Institute of Japan. Of course, the AIST is a great partner on that. And this is the, of course, in this institute, we have over 8,000 members. And of course, foreign members, over 100, I think, and 8 from the currently from the US too. We're trying to, in activity in this institute, we have the try to connect the academia and the industry. And of course, the leaders, currently, Professor Dr. Fujita switched from the Professor Fukuda, Vice President of the Nippon Steel. He's the president now. And Vice President is the, it's not really working, okay. Professor Nogami in the Tohoku University, And another vice president is Dr. Fukushima in JFE Steels. And I was the past ISIJ president. And for carbon neutrality in this institute, we try to clarify the issues and set the activity in the institute and promote basic studies and so on. And 3 years ago, we started the carbon neutral funding project. We tried to support about 20 projects in academia. So we are still extending such funding in our in ISIJ. Also, national project, again, for carbon neutrality is the GRAIN project. This is for hydrogen direct reduction project. And we've been steel industry working long time for on this. And industry consortium and combined with the multiple institute from academia. And here, of course, blast furnace applications and electric furnace applications. And starting from, for direct reduction case, we have also the mini mill type project too. So this kind of the project is going on also in the US and all over the world. Finally, I'd like to make short remarks. And importance of material science research, because I'm from academia, so scientific research is important, I think, for development of science and technology, and also for sustainable society in future. We do have the, for building safe and reliable society, we need to have the better life for the such kind of construction or the many kind of this social infrastructure. And also carbon neutrality is another target, and also the environmental friendly material development is also important, I think. So this is the, of course, in 2050, carbon neutrality outlook in Japan. We try to focus on the zero carbon emission in 2050. For the environmental impact, also the bottom one is the forecast of metal consumption in 2050 is expected. And here, when we look at this is the forecast from the Japan academia, and we need to have the 5 times more than current production. And also some of them, materials, we have different kinds of the element here. Some of them are already exceeded the potential resource in Earth. So we need to think about environmental friendly material development, not just focusing on producing new materials. And so recycling is, of course, important. Steel is rather better student on that. However, for non-ferrous alloys like aluminum, magnesium are difficult to extract the impurity iron element by the in terms of thermodynamics. So we need to work harder on that. And also, we usually have the global warming potential to discuss the materials production or from industry base. However, also we have another one, total materials. Total materials requirement. So this is another new kind of standard or measure. So we have to focus also about the measure for the material waste. So those two, recycling and also the mining and using use of the such resources, we have to think this kind of the different subject in both in terms of scientific technology and also industrialization too. So we need to work together on this kind of difficult task. So I hope we can have the good collaboration all over the world. So finally, I'd like to make the deep gratitude for my advisor and mentor. Two professors from the Kyoto University when I was a student, and also I worked for 15 years over there. Professor Imao Tamura, who really initiate the academic study in thermomechanical processing in Japan. And Professor Maki, and he is really a superstar for us and for microstructure control in steels in Japan. So our group, including my fellow colleague, Dr. Miyamoto, and we inherit the history of the research on the thermal processing in steels in over 40 years in Kyoto. My research group worked on for 20 years, so over 60 years history we are carrying on such heritage. And one professor in US, my thesis advisor, Professor Howe Aronson in CMU, I learned and I could deep fundamental knowledge of their phase transformation, not just in steels and the other metallic materials. So, and also special thanks to be expressed to the all the colleagues, collaborators, and students, and finally to my family. That's all I want to say. Thank you very much for your kind attention.
We do have a few minutes for any questions for Professor Furuhara. We have a microphone coming. Please tell us who you are.
Thank you for the presentation. Mario Micheli from Studios and Team. Great presentation. I enjoy all of it.
Thank you.
I'd like to talk, you discuss about the rapid heating and also some elements like manganese and nickel that can produce like functional materials.
Mm-hmm.
This is a really hot topic in academia, as you mentioned.
Yes.
Do you think that it's possible to produce industrially though? Because that's the challenge, how to jump from the lab to larger scale production of these functional gradient compositions. Thank you again.
Okay. So I think the part of the work and still research going on after the ISMA project, and also the steel company person working on the such issues. So now for sheet steel, I think the induction heating and online heat treatment is rather easy compared with the thick plate steels. So that can be done to use the control, use the such manganese heterogeneity in sheet steel applications. So also the for thick plate, that's for high nickel alloy. Of course, you can use again reversion case morphology dictate the nickel partitioning too. So that is very important issue for both plate and sheet steel applications. Okay.
What is your prediction about the future of hydrogen and hydrogen embrittlement that you referenced? Because the world is trying to move
Yes.
in hydrogen reduction direction. Can you comment, please?
Okay. So I'm not really a process metallurgy guy, so but physical